You're good.
Okay. All right, let's get started. Today's the 29th. And if you have a question, I'll tell you what, don't preface it by maybe this is easier, this is a stupid question, I think. They're never too, they're not. They're all good questions, okay? Every question is a good one. If you have a question, it's a good question. Go ahead, Louis.
Is y prime equal to, the derivative of y, right?
Okay.
So it's equal to the square root of x over 9y.
Okay, this is a little differential equation to solve for y. This is in, where is this from? Section, chapter, back in 5, right? 6.2, oh, the differential, oh, with the population growth, radioactive decay problems, okay. All right, a differential equation like this, what you want to do is say that's dy dx, okay, square root of x over 9y. And the way to solve a differential equation like this is to separate the variables. Get the y with the dy, the dx with the x. Okay, you can leave the 9 there, put it on the other side, doesn't matter where the 9 goes. Okay, then what we decided we're going to do is integrate each side. Consider that an antiderivative, an inverse operation to taking the derivative. The integral of y dy is y squared over 2. Now you get a constant here, but you also get a constant over here. And if you take the constant from the left and bring it to the right, you have the difference of two constants. And the difference of two constants is still a constant. Okay, so we're just going to make one constant on the other side here. Okay, square root of x is x to the 1/2. The integral is x to the 3/2 times 2/3. Well, we still got the 9 down there, plus a constant. Okay. Now, I'm not sure what form they want it in. If they want you to solve for y, you would multiply by 2 and take the square root if that's the answer they want. If they do, here's y. So what you would do is say y squared is equal to multiply by 2, so you get 4x to the 3/2 over 27. Now you get 2 times c. Well, guess what? 2 times a constant is still a constant. Okay? And then take the square root of each side. Boy, this is a kind of a poor problem here, but that's what you have. Okay. That would, I don't know what form they want it. Yes?
I got that same problem, and my answer was different.
Well, they changed the problems, they changed the numbers. So if your answer was different, then we know.
Same thing with x.
Where is it? Okay, and they want it in that form equals a constant. Okay, well, we can do it that way. This answer is the same as that answer. Here's what he's saying back here. If you multiply by 27, do they tell you how you want the answer? Yeah. At 27 times a constant, still a constant. And then you could write it this way. Is that what you ended up with? Yeah. Well, I don't. Unless they specifically say what form they want it in. This is a correct answer. That's a correct answer. That's a correct answer. So it'll take more than one answer. Now, sometimes it'll reject one thing and keep another, but that's basically it. Yes.
Looked up a problem like this online, trying to figure out how to do it. They're telling you to take y out as a constant.
What?
Like, can you do that? They're telling me to take y out as a constant, like 1 over y, and take it out to the outside of the derivative, like a constant.
No way.
No?
No.
All right.
No. No. Not good. Not good. Bad. Okay. Yeah, this is it. This is what you want. Any others? No solids of revolution questions at all? Wow. You guys are awesome. Or you guys are lazy. One or the other, okay? Or it could be both.
I have a theoretical question.
Go ahead.
What if you have x to
the second, let's y to the second equals y. And you did the revolution around the x-axis.
Well, there's a couple possibilities. First of all, you got a unit circle. And where do you want to go with this?
Around the x-axis.
Okay. Well, around the x-axis, this part's redundant because they will cancel out this part. So you really should have just the top half around the x-axis. Otherwise, the two just cancel out. Okay? So what you really want is y is the square root of 1 minus x squared. That's the top half of that circle. And then flip that around the x-axis. You want to do that?
Sure.
Okay. Here's what we got. If you take this, we're taking this area around the x-axis. And when we whip that around the x-axis, what does this rectangle generate? Disk, washer, or shell. There's only three possibilities. It would be a disk, thank you. The volume then is going to be pi. Now, we could integrate from -1 to 1 or go from 0 to 1 and double it. And I prefer doing it that way. Use the symmetry. We're going to go from 0 to 1. R squared. Well, what is R? This height. What is that equal to? Okay. That's square root of 1 minus x squared, but we're going to square it, so it's 1 minus x squared. Okay. So, 2 pi x minus x cubed over 3 from 0 to 1. 2 pi. Whoa, 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 whoa. 1 minus 1/3 is 2/3. Okay. And we end up with 4 pi over 3. Wait, something is not correct. What's that?
Isn't that the volume of the sphere?
4/3 pi r cubed. It is. Oh, it's a volume of the sphere. That's what we need. We've got a volume here. That's 4/3 pi r cubed, where r is 1. That's exactly right. Okay, thanks. Okay, that's exactly what we have. We got a volume of the sphere. All right, that's it. That would be it. We just derived the volume of a sphere. Wow, pretty simple. Any other questions? Okay, let's go on.
Oh, then with that, all you need is the diameter of this sphere, and you need to be able to find the volume.
All you need is a radius of a sphere or a diameter, and you can find the volume, which is 4/3 pi r cubed.
Yeah.
Yep. Okay. Let's do arc length, or length of a plane curve, as it's called. Arc length. Here's the problem. Problem is, given some function, f of x, let's say from a to b. Problem is, find the length of this curve. Length of that curve along the curve. If you were walking along this path, defined by this function, it's the distance traveled along that path. Okay? It's the length of the curve. Well, how can we do such a thing? Well, we can first approximate it by dividing this interval up into little delta x's. Okay? And what we could do is take a look at this here. Here's our function. Here's delta x. Here's our function. Let's say this is x sub I here, the ith x. Okay. Here's delta y. We could approximate the length of that curve over the interval by looking at the hypotenuse of that right triangle. Okay?
As x approaches infinity, that length eventually becomes
Yeah, that's exactly what's going to happen. As the delta x approaches 0, as the number of delta x's go to infinity, just what Chris said, okay? What's going to happen is these hypotenuses get smaller and smaller and smaller. The error goes to 0, and we have the exact length of that plane curve. let's do it. So the length of the curve, this ith piece, this one piece, is approximately equal to the square root of the delta x squared plus the delta y squared. Okay? That's what it's equal to. Well, let's sum up all these pieces, get the length in terms of n rectangles. We'll have this sum. Delta x squared, delta y squared. Okay. And then we can let the number of rectangles go to infinity to get the exact length. As n goes to infinity, please note the delta x's and the delta y's will both go to 0. But here's the deal. These are the ith piece. It doesn't matter really. Here's the deal. Is this in the right form for a Riemann sum? The right form for a Riemann sum is a limit as n goes to infinity of the sum as I goes from 1 to n of a function of x. This is f of x sub I times a delta x. That's not what we have here. Okay? We don't have it in the right form. What we have to do now is get it into the right form. Okay? So here's what I'm going to do. You ready for this? Jimmy's ready. Okay. I'm going to multiply by delta x and divide by delta x. Okay? And when I divide by delta x, I'm going to divide by delta x in this form. Square root of x squared. All the delta x's are the same. They don't have to be, but we'll call it delta x squared. Okay? Everybody okay so far? Boy, I'm already killing people off. Oh, I just started talking too. Holy mackerel, people are already dying on me. Ooh, this is not good. All right, let me go over here. We got room, right? So here's what I got. That enables me to write it this way. I know, it's warm in here. It's not me. See that? It's not me. It's warm. Whew. I have the quotient of two square roots. That's the square root of their quotient. I can rewrite this as delta x sub I squared over delta x sub I squared inside the square root. That's a 1. I have a delta y squared over delta x squared. I'm going to write it this way. Times a delta x. Wow, I'm getting closer. I got a delta x on the outside, at least. But my square root is still messed up. Okay. Here's my question to you. And I need a really super student to answer this question, okay? So I'm going to go next door. No. All right, so here's what... as n goes to infinity, okay? Let me ask you this. As n goes to infinity, what happens to delta x? Goes to 0, correcto. What happens to delta y as delta x goes to 0? No. Y is a function of x. We started with some y's, a function of x back here. Okay. As delta x goes to 0, what happens to delta y? It goes where?
Does it go to f of x? To like f of x?
Oh, like the other thing we did when they collapsed on it?
No, because it's like going to the function.
No. I'm asking for the change in y. As the change in x goes to 0, the change in y will also go to 0. They'll both be going to 0. But here's my question. Here's the real question. What happens to delta y over delta x as delta x goes to 0? What is that ratio equal to? That's
Undefined.
could be undefined. It may be undefined. It's possible to be undefined. But that's not the answer.
Determinant form.
0 over 0 is the indeterminate form. I cannot argue with that statement. But that is not the answer to the question. What is delta y over delta x as delta x goes to 0? What is that limit equal to?
Infinity.
It's the, well, wait a second. You can't just say tangent. It's not the tangent, no. But you're kind of close. What is it? You said something?
Infinity.
Infinity. It may be infinity, but it may not be.
Wait, why did I get a no when I said that? Should have made it.
What'd you say?
I said infinity. You're going to be right.
Did you say infinity? Oh.
No.
Wait, I was asking for the delta y part. I didn't ask for the ratio at that point. At that point, you were answering the question, what happens to delta y? And you said infinity. And I said no, because it's going to 0. Delta y is going to 0. Delta x is going to 0. The ratio is what I'm asking for now. So you have to. So here's my question to you again. I want to know the limit of delta y over delta x as delta x goes to 0. What is that limit equal to? Thank you. Yes. That's the definition of derivative. You said tangent. It's a slope of the tangent line. I mean, but the derivative is the answer. Okay. The definitive answer. It's a derivative. It's a definition of the derivative. That's what the derivative is. That limit. So here's what I have. The length of the curve is the limit as n goes to infinity of the sum 1 plus the derivative squared delta x. Now, guess what? We have all the ingredients here for a Riemann sum. We have the limit as n goes to infinity. We have the sum, I equals 1 to n. We have a function of x here. When we have y as a function of x and we take its derivative, that is a function of x. And we square that derivative, that's still a function of x. Add 1 to it, it's still a function of x. We take its square root, it's still a function of x. This is some function of x times a delta x. That is a Riemann sum. And how do we evaluate Riemann sums? With what? What? A calculator, is that what you said, Chris? That's a pretty good answer. All right, not the answer I'm looking for. How do we evaluate Riemann sums with?
Now.
Thank you. With an integral. Whew, boy, I'm working like a dog here. All right. That integral gives us the arc length of that function, the length of the curve, okay? Anytime we have a problem to solve in this chapter, okay, especially, and we can break it up into a summation of smaller parts that are going to 0 as the delta x's go to 0, all right, and get a Riemann sum, we can solve it with an integral, okay? That's what we do. All right, so let's do an example. Now, the bad news is this integral is bad news because there's not that many functions where we can take a derivative, square it, add 1, take the square root, and end up with something where we can actually do the integral. Okay? All right, let's do one. Let us do y equals 2/3 x to the 3/2. And let's have x go from 0 to 4. One of the very few problems where we can actually do this integral. X to the 3/2, 0, 0 here. Okay, at 4, where does it end up? At 4, it ends up to be 8 16/3, about 5. Yeah, no, it's something like this. Okay. It's probably more like that. That's all right, whatever. Okay. This is 4 16/3. Okay. We want to find the length of that curve. Yes, Carlos?
I can't see that.
Okay, thank you.
Because you push the button every time, it slowly tilts up, and that's why it's above the thing.
What happens? What?
Every time you press the button, it slowly tilts the thing up, and that's why it now goes past the space on the button.
Every time we touch what button?
Power button.
Oh, really? Oh, could be.
You can also just fill up the projection screen a little bit and that fix it.
What do you want me to do?
Well, project your screen a little bit and you'll get full.
We can deal with this. We can do it. Okay, let's do it. You ready? Here we go. Length of that curve. Is equal to the integral from 0 to 4. Square root of 1 plus the derivative. Now, what the heck is a derivative? 3/2 comes out front, cancels the 2/3, that's nice. X to the 1/2 squared dx. Okay? 1 plus the derivative squared dx. That's what we have. Length of that curve 0 to 1. Square root of 1 plus x. Whoa, that's nice. How do we integrate that? What form is it? Thank you. To u to the n form, where u is 1 plus x, the du is dx. Don't even have to multiply by anything. It's just u to the 1/2, the integral of which is u to the 3/2 divided by 3/2 times 2/3. Okay? From 0 to 4. Okay. So that's 2/3. Substitute in 4 plus 5 to the 3/2 minus 0, 1. Wow. That's your answer. 5 to 3/2, 5 squared is 5, whatever that is. Okay? It's one of the very few functions we can actually find the actual length of the curve because the integrals are just nasty. As a matter of fact, I don't know if you have one of these homeworks or not. You may. There is a class of functions that have been invented so that you can actually do the arc lengths with those functions. They have no other use other than to serve as functions where you can find their arc length. Because what happens is, they're kind of complicated, but you take a derivative, you square it, and you add 1, and what do you get? A perfect square. So you can take the square root of that perfect square and then integrate it. So be aware of that if you run across one of those in homework. I don't know if you have one of those or not. If you do, that's what it is. All right, any questions on this? Go ahead, Louis.
You took the derivative of x?
I took the derivative of my function, and then I squared it to get x. That's what I did. Is everybody okay? Okay.
Can we do one?
Can we do what?
Can we do one?
Yes, we did. What do you want to do? Another one?
Yeah.
Oh,
Well, no, I want to.
oh, you want to do one? Oh, be my guest tonight. You can do many. No, you can do one. Like I said, there's very few that. Okay, I'll give you one to do. Okay, let's do one here. Why don't you do this one? Let's say our function is y equals. What's that?
Tan x.
No, we're not going to do tan x. We're going to do 2x. Let's have x go from 0 to, say, 4 or 3. 0 to 3. You guys do it. You should simplify the radical in the end, too. Okay, how we doing out there? Somebody have an answer? Chris?
Y equals 2 root 5.
2 root 5. It's not quite what I got. So I did it in my head, so that means I'm subject to error. But I got, somebody have a different answer?
Square root of 15.
What is that?
Square root of 15.
Square root of 15, that's not quite what I got either. Yes,
3 square root of 5?
that's exactly what I got. So I agree with Karen, okay? And I disagree with Chris and Dylan. Anybody else want to get their 2 cents in here? Dan? I can see that.
I got root 5.
Root 5. Anybody else? Okay, let's take a look. Well, there's 2 ways to do the problem. One is with the calculus, and the point was to do an integral and use arc length. So let's do it that way first. Not the best way, but let's do that way first. Arc length is equal to the integral from 0 to 3, square root of 1 plus the derivative 2 squared for dx. That's equal to square root of 5. Take it out front. 0 to 3 dx. Well, the integral of dx is x. Substitute in 3, substitute in 0 to get 3 square roots of 5. So it is 3 square roots of 5. Okay. The other way to do it, go ahead.
I realized after you, it's a straight line.
It is a straight line. And given that it's a straight line, we could have done it by using a distance formula. The length of this curve is the distance from this point to this point, and the distance is the square root of 3 minus 0, 3 squared, plus 6 minus 0, 6 squared, is the square root of 45, which is 9 times 5, 3 square roots of 5. So either way works. I'm not sure if I have on the test a real simple example like this to actually do, which I may have, or a more complicated one where I ask you just to set up the integral. I think it's probably what I do. All right, that's arc length. Okay, you ready? Let's do the substantially more involved surface area problem. Here's the problem. Problem is we're given some function of x from A to B. Okay. We're going to whip this function about the x-axis. We're going to generate a solid of revolution. We know how to find the volume of such a solid of revolution. We're going to generate this. It'll be pi times the integral of r squared dx. Pretty straightforward. But what if we want to find the surface area? Okay, the surface area. You know, we found the volume. Did we do the bullet? We did the bullet problem, right? Finding the volume, but it would be important to find the surface area as well of that bullet. Okay, that would be an application. I actually did an application of this to some company in West Springfield that was making gears, and there were solids of revolution, and they had to coat it with this very expensive coating, acid coating of some kind. And they wanted to know beforehand how much coating was necessary, surface area of the thing, before they actually bid on the project and did it. So I had to do this. Of course, I charged them more than the project was worth, so they went bankrupt. No, that's not true. That's not true at all. I wish I had, but I didn't. All right, but anyhow, no, they were nice people. I'm only kidding. Okay, so we want to find the surface area of this. Okay, well, how are we going to do this? What do you think we're going to do to develop a formula that will allow us to find the surface area of the solid of revolution? What do you think we should do here? Where should we start?
We should find the volume.
Volume of? No, we don't need the
Arc length.
arc length. We're going to need that in the problem, but that's not the place to start. We want to do an approximation first, and then jump. And then what we want to do is end up with a Riemann sum. We can evaluate the integral. Now, the arc length is going to be involved in there. We will have to do that at some point. But in order to do an approximation of the surface area, we're going to start with what? Geometric forward. a rectangle. Let's start with a rectangle, okay? We'll start with a rectangle. Okay. Now what we're going to do is take an element of the arc length. I'm going to call that L sub I. I'm going to whip this rectangle around the x-axis. Okay? That L sub I, that element of arc length, okay, is going to get whipped around the x-axis like this. Okay? You with me on this? I want to find its area, because then I'm going to sum up all the areas that's generated in a similar manner. So, here we go. Oh, here it is. Here's the arc length. It's going to get whipped around the x-axis. Okay. It's like this. Something like that. Okay? Who cares? Okay, I want the area of that object. And here's what I'm going to do. I'm going to cut that. Okay? I'm going to cut this ribbon. Okay, I'm going to cut it and open it up. I want to find the area of that rectangle that I just generated, okay, by cutting that ribbon. What's the area of that rectangle? What is it?
Circumference.
Circumference of the circle times? No, delta x doesn't work here. You need, instead of delta x, you need the arc length. Yeah, we need the arc length approximation. The delta x doesn't work. That limit doesn't go to 0. The error doesn't go to 0 when you use that. But if you use arc length, it does. So it's the circumference times an arc length. That's what we need. So here's what we got. That surface area generated about the x-axis, okay, is going to be approximated. We're going around the x-axis first. We'll do one around the y-axis as well. It's going to be approximated by the sum of all these areas. Now, what is, here, let's call this, this is that radius, that's our function here. This height right here. So the circumference of that circle is going to be 2 pi r, the circumference of a circle. So it's going to be 2 pi r, and what is r? Here, I'll call it r. This is r. It's probably easy to remember if you remember it as r. 2 pi r, now in this case, r is the value of the function, okay, times the arc length, the element of arc length. And the element of arc length is what we did just before. Okay? That's what we have for the approximate surface area of that solid of revolution.
What is the R?
The r is this distance from here to here. It's a value of our function. It's the radius of that circle that's generated when we revolve this around the x-axis. Okay? It's a circle there. Go ahead.
You wrote your derivative as dy dx, not dy dr?
No, dy dx. Everything is in terms of x.
Oh, that was all. Oh, okay. Come on. Okay, after that.
Yeah. What is the exact surface area? It's the limit, as n goes to infinity, of the sum of all these approximations. But when I take the limit as n goes to infinity, what is that thing here? What is this sum? What kind of sum is it?
A Riemann sum?
Thank you. It's a Riemann sum. And we can evaluate that sum with an integral. This sum is the area under some curve, namely that curve whose function is this. See this thing here? I can replace all that with g of x, say. So what do I have? A Riemann sum in g of x. Okay? That g of x is going to generate some function. How do you find its area? With an integral. How do you evaluate this? With that integral. So surface area about the x-axis is the integral. 2 pi a to b r square root of 1 plus the derivative squared dx. Okay? That's the surface area of that solid of revolution when we take that function around the x-axis. Okay? It's surface area. Okay, here we go. You ready? Let's do a problem. Well, let me give you the other one. I'm also doing the other one. That's about the x-axis. Let's suppose we would take the same thing around the y-axis. I'm going to keep my same rectangle. I have a delta x there. So everything will be in terms of x. When I take this rectangle around the y-axis, everything is the same except for one thing, the radius of the circle. The radius of the circle before was our function. Okay, I called it r sub I, was our function. Now the radius of that circle is the distance from that point to the y-axis. This is our new radius. If I'm going to go around the y-axis, this is going to be my radius. What is that distance from the y-axis equal to? X. Good job, man. Nice. The only difference between going around the x-axis and y-axis is this. You got an x here. Because that's what the radius is. Okay? Okay, you guys ready? Let's do a problem. Sam, you ready? Okay. Have you heard back, Sam, from that?
No.
Not yet? Oh, it's not March. Tomorrow's March.
There should be a release of some information soon, but.
Yeah, okay.
What that is.
Yeah. Did I write you a recommendation? Don't forget it, you're not getting it.
Actually, professors, not that you are.
All right, let's go. Let's do a problem. Here is the problem. Let's take a line like so. Okay. Let's whip this line around the x-axis. 0r. Okay, 0r. When I whip this line around the x-axis, we will generate what? A cone. We already found the volume of this right circular cone. I think that was one of the first volume problems we did. But now what we want to do is find the surface area. And actually what we're finding is called the lateral surface area, because we're finding the surface area generated by the line, not including the circular base. If you wanted the total surface area of the cone, you'd find the lateral surface area plus the area of the base, pi r squared. Okay, just tell me. Does that make sense what I'm saying? Okay, we got this line. We're going to whip it around the x-axis. Okay, we have this line. We're going to whip it around the x-axis. We're going to generate this cone. Okay, we want to find the lateral surface area. That's the area, surface area generated by the line itself, not the area of the circle here. Okay, that's what we're finding. Okay. Okay, does anybody know the formula for the lateral surface area of a right circular cone? No? Oh, so whatever we got is going to be the correct answer. Okay.
In this case, it's a triangle, and you have 1/2 based on height.
Well, that's the area of the triangle, but that's not going to be the lateral surface area of the cone. You could look it up, that's true.
It has a pi in it.
That's true.
Oh, pi r square root r squared plus h squared.
Yeah, very good. Wow.
Good find out.
It is. Let's do it. We're going to derive the surface area, lateral surface area of a right circular cone. So let's do it. Okay, we got to find our function first. What is this function equal to?
R over H.
What is it?
R over H times X.
I missed the very first word you said.
R over H.
I missed the first word.
R over H.
Yeah. Negative r over hx plus r. Good deal, Brendan. Okay, that's the equation of that line. We're going to whip it around the x-axis. We're going to generate this right circular cone. And what we're doing now is finding the lateral surface area of that right circular cone. Okay? All right, so let's take a look. The surface area around the x-axis is equal to 2 pi times the integral from 0 to h R. What the heck is R? R is this here, right here. What is that R equal to? Yeah, which is? Thank you. That's your f of x right there. That's the r. That's the radius that this thing is going to get whipped around. Okay? An element of the arc length, the square root of 1 plus the derivative. The derivative is negative r over h squared is r squared over h squared dx. Whoa. Wow. This integral will give us the lateral surface area of this right circular cone. Okay? Let's do it. So 2 pi. This is a big constant here. Matter of fact, I'm going to write this. I'm going to take h squared over h squared, combine this into 1, and get the square root of h squared plus r squared over h. Okay? Everybody see that? I just multiplied by h squared over h squared, added h squared plus r squared. That's this. The square root of h squared in the denominator becomes h times the integral. Okay? With me? Nice. 2 pi square root of h squared plus r squared over h. The integral, negative r over h x squared over 2 plus rx from 0 to h. Whoa. A nasty problem. Nasty. We get 2 pi square root of h squared plus r squared over h times, let's substitute in h. We get a negative r over h, h squared over 2 plus rh. Substitute in h. Now substitute in zeros to give me 0. Okay? Check it out. How are we doing? Doing okay? Hey, you doing all right? Good. Okay. That's equal to 2 pi square root of h squared plus r squared over h. Now, one of these h's cancels, so I get a negative rh over 2 plus rh. Well, if I take a negative rh over 2 plus rh, I get rh over 2. Multiply by 2 over 2 here. So you end up with rh over 2. So you get 2 pi square root of h squared plus r squared over h times rh over 2. That's what this is. Holy mackerel. So h's cancel, 2's cancel. We get pi r square root of h squared plus r squared. Now, wait, Dylan, what did you read for the lateral surface area of a right circular cone? And make sure you only had the lateral surface area, not the total area.
Oh, I'm sorry. I read the one for the right circular cone. Lateral surface area.
Yes.
Wait, of a cone?
Yes.
Yeah, pi r times the square root of r squared plus h squared.
Okay, there we go. This is sometimes called the slant height of the cone. It's this distance right here. Okay, sometimes that's called S or L. Okay. But that's it. We have derived the surface area of that right circular cone. Now, let's suppose we whip the same line around the y-axis. Wait a second. You guys can do it. Here's what I want. The lateral surface area of that right circular cone when this is whipped around the y. Will it be the same as this one? No, it will not. So, you guys do it. I want you to whip this around the y-axis this time.
Would the volume be the same?
The volumes are not the same, no. Nor the surface areas. And you're going to find the surface area. Is it up there somewhere, Jacob? Oh, okay.
Are you sure the volume would be the same?
Volumes are not the same. The volume of a right circular cone is 1/3 pi r squared h. If you go around the other way, the h and the r switch places. It'd be 1/3 pi h squared r, because the h becomes the r and the r becomes the h. See, as you whip it around the x-axis, this distance is the r, right here,
Oh,
up the y-axis. The other way, it's the
I
h.
was thinking about it wrong.
That's okay. Go ahead. I want the surface area of that right circular cone when that's whipped around the y-axis this time.
I was thinking of it in 2 dimensions instead of 3.
Yeah, there you go. Wait a second. Hey, were you here last time? And Mohit was? Oh, I understand now. Why should both of you have to suffer? Oh, man. That's a good plan, actually, though. I see. One goes, the other stays, and it works out. No.
I don't know where she is.
Okay.
He said the same thing about you last time.
Yeah, you did. No, that's okay. I'm only kidding. I tend to do this. You're finding, whoa! You're finding the lateral surface area of the cone, the right circular cone that's generated by revolving this line about the y-axis. Actually, we don't have much more to do.
You said the test is when?
A week from Thursday. March, I don't know what. First, second, third, 10th, I guess.
Or 24? So it's going to be on this surface area. Arc length.
Area between two curves. Volumes of solids of revolution. There'll be a few of those. Arc length. Surface areas. Work done by a spring. Centroid of laminas of constant density. And a fluid force at the end. Easy stuff. That's what we do.
It's going to be still multiple choice.
What's that?
It's going to be multiple choice.
It's going to be, the format's identical to what it was the first test. It'll be done in sections. First section, a couple where you have to find the area between two curves. Another section where you have 4 or 5 to find the volume of those solids of revolution. And then a couple more arc length surface area ones, maybe set up the integrals. And then work done by a spring, a couple problems there. Centroids, 2 or 3 in that, and then fluid force.
Or still going to get like a practice test or no? For this one?
Yeah, probably. I'll whip one up. I can do it. Yeah, I'll do it. You, Lewis? I would do it.
Helps me see we're in a week.
Okay.
Everywhere.
No, that's not true. That's not true. That's not true. Do 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 do.
Oh.
Did you get it?
Someone's the same thing.
What's that?
What's different about this than the last one?
Well, it's a little bit different. We're going around the y-axis, so the radius now is not the function, it's just x. That's the difference. So it's easier. It's an easier problem. How are we doing out there? Who needs more time? Oh, okay. Take another couple minutes. Okay, how we doing? How you doing, Dylan? Doing okay? You got it? Maybe. Who's got an answer he or she is pretty confident in? Oh, when I do this, it means you raise your hand. Okay, if you have an answer you're pretty confident in. That's what this means.
Is it just pi h square root h?
Yeah, exactly.
Yeah.
That's exactly. Now, did you just use your brains to figure it out, or did you do the thing out?
I halfway through I kind of figured it out. But I stole your work in the first part and brought that whole concept.
That's okay. That's quite all right. Quite all right. Is that reasonable? All right, let's do it. Is that what you got, Carlos? Oh, you didn't? Oh, okay. Let's do it. Karen, did you get that? Ooh, that look means no, huh? Okay, that's okay. All right, let's take a look. This time, when you take the rectangle here, and you whip it around the y-axis, this is the radius, okay? And that distance, that radius, okay, of that circle that's generated is equal to x, the distance from the y-axis, as opposed to going around the x-axis, where the radius here is the value of the function. It's the y, okay? It's the y. So, the surface area about the y-axis. Now, if you think about it, what's going on? You got a right circular cone again, but what's the radius of the base of that right circular cone? It's h now, not r. Before, when we went this way, the base had a radius r, and the formula was pi r square root of r squared plus h squared. It's the land height. Now, when we go this way, it's the h, that's the radius of the base, and it should be pi h square root of r squared plus h squared. Well, let's do it out. 2 pi, the integral. Now, when we do this, I'm still taking this rectangle. I'm still using delta x. Everything is still in x, okay? It's still in x. When I take a rectangle this way, the delta x, that determines everything over here. It determines the method that's used. It determines the variable that's used, the limits of integration, what's used. So what is the radius? It's x. X is going from 0 to h. Okay. Square root of 1 plus the derivative. Well, we had that. That function was negative r over hx plus r. The derivative is still the negative r over h squared dx. The only difference is this x now is the radius instead of the function itself that we had from before. So we get 2 pi. And again, I'm going to take h squared over h squared, square root of h squared plus r squared over h. The integral of x squared over 2, 0 to h, we end up with 2 pi square root of h squared plus r squared over h times h squared over 2. 2's cancel, h's cancel, you get pi h square root of h squared plus r squared, which is what you would expect to get. Okay? We all set on that? How are we doing? Carolina, how are you doing? You okay? Dylan?
Sort of just feeds back to the revolution with the volumes. So sometimes when instead of finding something on the x-axis, we're finding it about the y-axis, the equation actually simplifies that we use because we use x, not f of x.
Yes, that's very true. Very true. Okay, we all set on this? Because I'm going to go on. We got one more topic to cover. Question? No. All right, ready? Let's do it. This is work done by a spring. Whoa. I don't know what section is this? What is it? 7.5? Is that where I'm at? 7.5? Brendan, am I at 7.5? Spring? I think the spring is right after surface areas, right? Or is it central? I don't know what's next. We're going to do springs. What's that? 7.5. Okay, good. Thanks. Okay. Here's the deal. We have a spring hanging from a wall, hanging from a ceiling. Okay. It's got a natural length, just with no weight attached. Okay, whatever that happens to be. When we attach a weight to this thing, it's going to stretch the spring. When we put a certain weight on it. Okay. And according to Hooke's law, the force is proportional to the distance it's stretched. The more you stretch the spring, the more force is required to move it an additional amount. Okay? X is the distance from its natural length, how much the distance it traveled. We want to find the work done in moving this spring from some point to another point. Whether it's natural length, stretching it 4 inches beyond natural length, or have it already stretched 4 inches beyond and stretch it an additional 2 inches or whatever it happens to be. We want to find the work necessary in doing that. Well, work is a force times a distance. Okay? This is Hooke's law right here. The force is proportional to the distance. It's already been stretched. The work is force times the distance. Okay? These are basic concepts, basic physics things. Okay? we want to find the work done in stretching it, let's say from natural length to some other distance here. Well, let's take a look at that. Let's suppose, let's find the work done over a small interval here, this little delta x. How much work is done in moving it from here to here? This piece of work is approximately equal to the force times the distance, which is delta x.
But doesn't it increase over time?
Yes, it does. And down here, the work over here will be its force times that distance, delta x. And the force is increasing because as the x's increase. Very true. I'm going to sum up all these pieces of work. The work, total work done in stretching it from here to, say, here, is the sum of all these little pieces of work. Okay. These little pieces of work, which would be F delta x. Okay. But what is the force equal to? The force is equal to Kx is proportional to the amount of distance. Okay. So, what's the total amount of work done? It's the limit, as n goes to infinity, of the sum of all these little pieces of work. Okay. Whoa, what kind of sum do we have here? What is this sum? What kind of? What?
Does it start with an R?
Yeah, it starts with an R. Yes, that's what kind of sum we have. We have a Riemann sum here. This is a Riemann sum. We got the real simple one too, because we have k times x. That's a function of x. It's just some constant times x times a delta x. It's a Riemann sum. How do you integrate it? How do you evaluate it? With an integral. That's the work done by that spring as it moves through that distance. Now, here's the question. You don't know what k is. You have to be given some information in the beginning of the problem to solve for k. Okay? That's what you're going to have to be given. And that k is determined by the number of coils, the material, the thickness of the spring, all kinds of things. But you have to be given some piece of information. For example, typical problem would be something like this. Let's say a 10-pound weight stretches a spring half a foot. Okay. Use foot pound. You could use inch pounds. You can use whatever you want, grams and centimeters and all kinds of stuff. We're not particular about the kinds of units.
Pounds per inches.
What's that?
Pounds per inches.
Yeah, well, I use half a foot. I'm going to end up with foot pounds
Could
of
you
work.
find K from this?
What's that? Yes. Let's do. Now, that's the first part. You're going to be given that. This is going to enable you to solve for k. Then the question is, there's a couple questions that are possible. Let's ask a few questions here. One question. How much work to stretch it an additional 1/2 foot? Okay, there's one question. Here's another question. Remove the weight. When you remove the weight, the spring goes back to its natural length. Find work in stretching it two feet beyond natural length. And the third question I want to ask is, remove the weight, same as number 2, but find the work in compressing it 2 feet. Okay?
What are we considering x?
What's that?
What are we considering x?
X is a distance that's stretched beyond natural length.
So work is f of x.
The work
Fx.
is the integral. The force is kx. I'm going to do it. Let me do it. You ready? Then I'll give you guys a problem to do. And then we'll see where we are. Okay. Okay, you ready? Here we go. All right, the first thing you're going to have to do in these problems is to find k. Okay? Okay? This is by Hooke's law. Force F equals kx. Okay? What are we given? We're given the fact that a 10-pound weight, that's our force, stretches it 1/2 foot. Okay? K is equal to 20. That's the spring constant for this spring, 20. Okay? Next, number 1. How much work to stretch it an additional 1/2 foot? That work is equal to the integral. Now, we're already 1/2 foot beyond. We're starting at a 1/2 foot beyond, and we want to go to 1 foot beyond. Okay? Everything is measured from natural length. That's 0. Okay? We're already at a 1/2 foot beyond, so we started at 1/2, we're going to 1 foot beyond. And we have to integrate. What's our integral? It's kx. We got k, 20, x dx. Okay? So, the integral of 20x squared over 2. Okay. We end up with 10 minus 10/4, 5/2. We end up with 15/2, 7.5 foot-pounds of work. Now, am I over the edge there? Yeah, probably. That's my answer. 7.5 foot-pounds of work. Be all set on that? Okay. Number 2. What we're going to do is take the weight off. The spring goes back to its natural length. We want to know the work in stretching it 2 feet beyond that natural length. So, what are my limits of integration here? 0 to 2. Still 20x. 20x squared over 2, 10x squared. 0 to 2. 40 foot-pounds of work. Okay? That's how much work is required. Now, we're going to take that weight off. It goes back to its natural length. And we're going to find the work in compressing it 2 feet. Whoa. Well, go ahead.
So obviously, since stretching is one force, then to displace it in the reverse means that it's going to just be negative. So
Yeah.
can you just draw negative?
Negative 40 should exactly be the answer. You're totally right. What he's saying is, if we're going to go in the other direction, shouldn't the work be just a negative 40? And that's what we're going to find out.
Well, how do we know if there's enough space for it to actually be compressed?
We don't know that. You're going to have to assume that there is. Yeah, obviously, if the natural length is 1.5 feet, we can't stretch it 2 feet. Okay, but we're going to have to assume that we can. Okay.
Big spring.
Yeah, a big spring. Yes. So we're going to go from 0 to negative 2 this time. No, you know what? It's going to come out exactly 40 foot-pounds of work again. It's not going to matter to it, I think.
Say you just pull out the negative like I got.
Yeah, well, let's see what happens here. This is kind of interesting. 20x squared over 2, you get 10x squared again, from 0 to negative 2. You're still going to get 40. You're still going to get 40 minus 0. You still get 40 foot-pounds of work.
Because of the square. It makes it so.
Yeah, that's right. Because
It's not
of,
the other way from 0 to 2, so you get the negative.
what's that?
You don't do
Yeah,
it from
it's
0 to
2.
0 to negative 2,
Because
so
then
you
you
get the
have
negative
minus
work.
40.
But you
0
can't have-
minus-
Well, if I go, I'm going from A to B, start to finish, 0 to negative 2.
Yeah.
And that's the way I should do it. And so you substitute in negative 2 first, and
And you
then
should be able
substitute
to
0.
have negative work in this scenario.
Well, yeah, you can have negative work. If I did it this way, if I went from -2 to 0.
That's what I was saying.
Yeah, but see, that means what? Here's the spring, and now, if I'm going to go from -2, what I'm going to do is compress it to -2, and then let it go to 0, and that way. But that's not what we're saying. We're saying start at 0 and push it up. Yeah, so it's going to be 40 foot.
You can't have the negative work.
Yeah, not in this context. We wouldn't have it. All right. So you guys ready to do one? Okay. Let me give you one. Okay. These are all the same, these spring ones, so not a big deal. So let me give you one. Let's say we have, let's use kilograms. Okay, let's use kilograms here. A 50 kilogram weight stretches a spring, I don't know, 4 meters. Okay, 4 meters. So the spring is there, you put a 50 kilogram weight on there, stretches at 4 meters. Okay, it doesn't wreck the spring up though. Okay. Okay. How much work? Work done in stretching additional 1 meter. Remove the weight, have it go back to 0. Work done in going from 0 to 10 meters. Yeah, they're all the same, these work problems. You'll see that in the homework too. Yes?
10?
10. 10 meters, yeah.
No, what's 10?
You're going to find it.
Oh.
Wait, did I give you some? Yeah, 50-pound weight stretches at 4 meters. That enables you to solve. Then how much do you work is done in stretching an additional 1 meter and work done in going from 0 to 10? Then we have 2 topics next week. Centroid laminates, that's kind of cool. And then the fluid force thing. Done. It's good stuff. You protesting, Brendan? Is that it? Oh. I saw your lacrosse people out there. What, Sunday? Sunday morning. They're out there practicing lacrosse.
I was out there practicing baseball Sunday too.
Really? Wow. Pretty cool. I didn't notice the baseball players, but I did notice the lacrosse players. It's not too early to practice, but well, the weather's nice and all that. Last winter, this time, we probably had 3 feet of snow still around. Actually, I watched the Red Sox today. Play BU and then they play Northeastern. I didn't see that game, but the BU did. Got him?
I think so.
Good.
Unless I found K wrong. Unless I found K wrong, which is possible.
No, that's not possible. Okay, how we doing out here? Who wants more time? Okay. You got it?
I think so.
How'd you do tech? Competition.
Apparently better than I thought it did.
Really?
I don't know, I got like 10 questions done.
Wow, that's quite a bit.
I
You got 10 done. How many did you get right? Yeah.
No, I only went through, I only got an answer. I thought, recently I had this session.
Wow.
I just did with the dance it. Just like, knock off the ones. Like,
Yeah.
A bunch of them I looked at and was just like, no.
Yeah.
Not even going to waste my time.
Wow.
And then there's a couple of them that were kind of,
Well, cool. Nice.
I actually thought I spent too long answering the question. I was like, we get through more and but it just worked.
Good. Hey, sounds good.
It doesn't count everything, it's in a degree, so
What do you mean doesn't count?
if you have a 2-year degree, it doesn't count.
Oh, you do have a 2-year
Yeah, I have
degree.
a business degree.
Oh, did you put that down on there?
Yeah, it's intense.
Just Gene knew that, right?
I think so. And when I did it today, it sort of reminded me that this happened last time that I took it.
Oh,
That it didn't.
yeah. Yeah, okay, so what? You came to practice, you have a good time, you do some problems. It's good. It's all good. Okay, everybody all set? Dan, how you doing? You need another minute? Okay. Okay, let's take a look. Let's find K. What is it?
Well, 12.5.
12.5, 25 halves.
Oh, yeah, 12.5.
What's that?
25
Yes. Okay. Hooke's law, force is proportional to the distance it's stretched. Force of 50 kilograms.
Burns, like speaking in physics, that's not a force.
Yeah, I know. We get units. So you want to use,
You gotta multiply by 920.
yeah, we don't do
Well,
that.
depending on how general.
When you do the problems on WebAssign, it'll give you the probably the right units.
Yeah, it's mainly in like customary stuff, not metric system.
Yeah. Oh, you mean feet
Like
and
foot pounds and stuff.
foot pounds.
Right.
So you're saying, Burns, you should have stuck to foot pounds? Is that what you're saying,
I
Brendan?
mean, that's what you want to do.
Yeah. No, I want to, maybe that's what Carolina did. She switched to the right. Wait, what do we got? What's the unit? The newtons or something? Or what do we have? Newtons? Okay. We're going to use kilograms. Thanks. All right. K times X is 4. Divide by 4, both sides. So 25 halves, that's K. All right, once we find K, we'll find the work done in stretching it an additional 1 meter. So we're already out there 4 meters. We want to go to 5 meters. Okay? K, X. So take the 25 halves out front, X squared over 2, from 4 to 5. We're going to have 25 fourths. We're going to have 25 minus 16. We're going to have 9. Okay, so we get 225 over 4. Nice answer. This will be kilogram something, whatever the units are. Work units would be what, joules or something?
Yeah.
Fine, joules. How's that, Brendan?
Well,
No.
Yeah, I know.
right units.
Well, we're going to use work units, whatever they are. Second one, find the work going from 0 to 10. You a physics major or something, or what? Oh, no? A purist? Yes. Well, it's good to be a purist. You shouldn't be. All right. Now, we're going to remove the weight going from 0 to 10. Integrate 25 halves x. To get 25 halves, x squared over 2. 25 fourths times 100. Oh, this one has the decency to work out, right? 400 to 100, 25 times 25, 625. Whatever the work units are. I'm calling them joules.
If you're looking at it in decimal form, it'd be 6.25 x squared. So
It'd be what?
6.25 x squared, if you didn't use the fractional.
Times 10 squared. All right, whatever. 625. Okay, so Thursday, 2 more topics to cover. Okay, centroids and fluid force. And so your homework should be through 7-5. Okay, 7. See ya.
Good night.
Hey, we'll see ya.
Those actually stick.
See you, Burns.
Well, you'd have to do this in pieces.
Going to the beginning.
Because you don't have a single function in here. You do this piece plus this piece and double it. You'd have to do it in pieces. That would work.
Every single one of them will be just wire the constant.
All right, who's our mathematical people now? Yes.
Like,
Yes, I did get it. I have it.
We started the lab thing, so what is this? Does it do or?
It was due Friday. But take it
I
to
had
another
a
day.
quick constant, that's why I didn't like.
All right, so you have the labs. You have mathematics?
gotta figure out what I can do.
No.
Go to the stick.edu/math. Get Mathematica.
It has to be in PC or it can be in any computer?
Any
Okay.
computer. So do that, get Mathematica. So what did you do? You emailed Carlos Pedro, and he wasn't there, no doubt. So he's gonna get in touch with you. And then hopefully he can come up with something, where you just do this and it works. And he's good at it. So he should be able to just tell you, just do this and do exactly what he says. And you should do it.
Whatever it works, kind of. He was like, you don't need this, you don't need this, you don't need this. He was very, like everything, like everything.
For the last one?
Yeah.
Yeah, because the one we're turning into is
Earlier. I know, and then he helped me a little bit with that one. He gave me like the first do well thing.
Yeah, so what did you have, because
Oh, good. Oh, okay, so this will work
What did you
out.
have for your first Y? Was it like blank,
Okay,
basically?
so, okay, so here's the
Do you
deal.
want me to just send it to you?
You come in.
Sure, because I was looking at one where it was like,
And I'll be around.
there was like a similar thing,
Look under rocks.
and it just said while,
Find
and it's
me.
like, essentially no, it's just.
I'll either be in my office
Because if you had
or
So you would put, it's something
4:15.
like.
If you can tell me what time you're gonna be here,
Count
I can make sure that, I can tell you where I'm gonna be.
Then you have to put
Because
like
I'm either
numbers
in
bigger than the
413
max,
teaching or
then
I'm
that
in my
becomes the
office.
max. It's like
Then I
one
have
line,
help
it's not
3
a lot.
next door, and that's at Thursday, that will be at 12:30.
Oh.
If it's as late as that, it'll be
We got it
at
till
6. But up to then, it's either my office or the floor.
Okay, all right.
And then I'll give it to you in the test center, and you can just do it.
Okay.
We can do this.
Where's the link to the actual lab? Like, did you send an email? Or?
I sent an email to a link to my Dropbox, okay? But you gotta put it in the URL as a single line and not break it. Make sure it's not broken. If you can't get the labs, send me an email. I will send you all the labs to you directly.
Okay, sounds good.
Would you mind extending some of the chapter 5?
Okay, send me an email. You send me an email, I will do it. Send me an email.
And will these
So-
notes be up?
Is that what?
Will these notes be
These notes will be up, let's see, when will I see? Oh, jeez, it's a month, it's still Twitter.